All right, great. Welcome, everyone. For those of you who don't know me, my name is Federico Menozzi. I'm a senior computer science major here in the department, and today I'm going to be talking to you about the research I did this past year in virtual presence for medical procedures. This past year, I was fortunate enough to work not only under my advisor, Henry Fuchs, but also alongside graduate students Youngwoo Cha and Rohan Chabra as a member of their team. So our motivation really centers around the observation that physical presence is the best way to learn how to perform a medical procedure. There's really no better way than being there with the doctor in real time watching him work. But this methodology comes with a couple of challenges. The first is really that this isn't really a feasible model for fast-paced or impromptu procedures that you might find in an emergency room. You really can't risk patient safety by getting everybody set up for a learning experience. So there's really no way for students to get hands-on experience with that. Additionally, some procedures may use equipment that's not available to their institution. UNC Medical School is pretty well funded, so this might not be a problem for them, but you can understand that maybe a smaller, less funded institution might run into this problem. So our solution has been to simulate this physical presence with virtual reality. And the way that we do this is by capturing a procedure, creating a series of 3D reconstructions that we later play back at a frame really similar to video, and then you walk around in this new dynamic environment to simulate this physical presence. This past year, we focused on prostate biopsy as our case study. The reason is that prostate biopsies are very common. I think there's over 1 million of them performed in the US alone. So we can collaborate frequently with the UNC Medical School. And in fact, we have on several occasions collaborated with Dr. Eric Wallen and others in recording actual prostate biopsies. So temporal 3D reconstruction, as it's called, is not new. We've seen this in technologies like Kinect Fusion, whereby you use a series of Kinect cameras to capture objects as they move through a dynamic scene, and then find correspondences between features in the objects so that, for example, if I track my arm around the room, it'll track the correspondences between features, and then we can ultimately deform these correspondences and obtain a high-quality mesh. This technique, Kinect Fusion, was used extensively in a paper entitled Temporally Enhanced 3D Capture for Commodity Depth Cameras. This paper was actually authored by a former UNC PhD student by the name of Ming-Song Du. And we base our work heavily off of Ming-Song's paper. So he uses Kinect Fusion as well as a number of other techniques to sort of, with the end result being sort of what we're looking for, a series of reconstructions that you can later play back to simulate presence. As far as VR in medicine is concerned, there's actually a body of evidence that supports this notion that supplementing training with virtual reality in some way prepares students to perform procedures faster and with fewer mistakes than control groups that had no such access to this technology. So now we're going to move into our pipeline, which can roughly be divided into 2 phases. The first phase is the temporal 3D reconstruction, which I've talked about a little bit in the prior work. This has been done mostly by the aforementioned graduate students, and it revolves around combining static background data with dynamic foreground data to produce a series of 3D reconstructions. Once we've created these reconstructions, this is where I come in what we call the post-reconstruction enhancements. So given these reconstructions, how do we enhance them to be useful in a medical training context? And there are a number of ways that we've gone about doing this, which I will describe shortly. So the first stage of the temporal 3D reconstruction phase is the static reconstruction. So the goal here is that we want to create a single high-quality 3D mesh of the static background. So the static background would be all of the things in the scene that don't move or deform during the procedure. So this will be things like the floor, the walls, large furniture, etc. And so the way we do this is we use a single mobile handheld Kinect. We slowly sweep the room, and we generate a sequence of color and depth images with the goal of eventually using sort of feature matching to compare features across frames and generate a single 3D mesh. So this is an example of such a mesh. This is of a room that we actually built up in the telepresence lab. That's a 1-to-1 scale replica of the room at the medical school where they perform prostate biopsies. So you can sort of see what I'm talking about here. We've got this static data, the floor, the walls, large furniture like the bed and the table. And it's fairly accurate. You can see features like, for example, up in the poster and the wall have been preserved at least enough to be recognizable. So once we've created the static scene, we have to actually incorporate the dynamic data. So as opposed to the static scene, which is done before the procedure and uses a single Kinect, the dynamic sequence is actually recorded as the procedure unfolds with a series of fixed Kinects that are mounted on the walls. Just like the static reconstruction, we want to capture a sequence of color and depth images with the goal this time being to construct a 3D reconstruction per frame. So we take multiple views from all the cameras, and we create a single 3D reconstruction for every frame of video. So you can see that if we capture these at a similar frame rate and then play them back at that same frame rate, we can sort of emulate 3D movie effect. One of the graduate students I mentioned earlier, Rohan Chabra, this past year worked on ways of improving the quality of these reconstructions. I'm not going to go into too much detail about that, but it basically revolved around how best to optimally place the cameras to minimize occlusion and sort of maximize the areas that we want to see, and then how can we apply texture mapping from the RGB images to increase the resolution of the resulting mesh. So here we are. This is an example of a 3D reconstruction. These are 3 views of the same reconstruction. One thing that I do want to point out is that any static residual background data has been automatically segmented out so that we're only left with the dynamic portion of the reconstruction. And this will become apparent when we have to align the two together. So here, once we've captured all of these sequences, we've created all these reconstructions, we need to incorporate the static background data into each of the dynamic foreground data to create the resulting sequence. So here, for example, in A, we've got a sort of the raw result of a reconstruction of a dynamic frame. So you'll notice that we've got not only the 3 participants here, but we've also got a lot of residual noisy background data that's not very high quality. Compare that here in B to the static reconstruction that we created earlier, which is much higher quality. In C, we segment out this background data so that we're only left with the dynamic foreground before finally fusing the two together in D to create a single snapshot of that instance in time during the procedure. So now that we've got these reconstructions, this is where I come in. How do we enhance them to be useful for medical training purposes? So the first thing we looked at was scene annotations. These are 3D text annotations that appear in the scene with the idea that we want these to be useful as training instructions or reminders so that the student knows at any given point during the procedure what it is that they're expected to be doing. So this is an example of a sample frame viewed through an Oculus headset and rendered using the Unity game engine. You'll notice here that we've got the static background data incorporated into this dynamic frame. And then in addition, along the wall, we've got this scene annotation. So this appears as 3D text in the scene. It's fixed in the scene. And in reality, it'd be something more useful than greet the patient. But you can understand that given the proper context, the student could at any point look up and know exactly what they're supposed to be doing. So the next is playback controls. I've sort of alluded to how this can be seen as a sort of movie in 3D. And so like any regular movie, we'd like to be able to control how it is that we play back through the frames. And so the idea is that we introduce a sort of heads-up display element that allows you to control the playback of the frames. This is sort of one of the more important contributions that we made here in the sense that this is sort of what distinguishes virtual presence from physical presence. When you're watching a real procedure, you can't stop and rewind to review something that you may have missed. You can't fast forward through a portion of the procedure that you may already be familiar with. So this is another view of that frame. We've got, again, the annotation. We've got the static and dynamic data. And then additionally, we've got this new floating heads-up display element. So unlike the 3D annotations, which are placed in 3D space, the playback control panel actually forms a part of your heads-up display so that it floats in front of you and is always visible no matter which way you're facing. You use a wireless mouse to control it. So you use the scroll wheel to select your function and a left click to activate that function. And if at any point during the procedure, the playback control panel becomes obstructive to your viewing of the procedure, you can right-click on the mouse and the panel will disappear. And finally, we have 3D models. So the idea here is that we thought that, in, for example, a prostate biopsy, it would be useful if a student could consult a reference anatomical structure of the human prostate. So we introduced this ability to introduce new 3D models directly into the environment. Much like the playback panel, the models can also be toggled on and off so that they don't obstruct you during key parts of the procedure. And like I mentioned, this is definitely useful to reference during a procedure. So here we've got an example of a view of that same procedure before and after we introduce a new model. Unfortunately, I was unable to find a model of the human prostate. So obviously, the human heart is not super relevant for this procedure. But you can sort of see what I'm getting at here. This model is in 3D space. So if you turn around in your head mount, you can view it from multiple sides. And so, one thing that you might want to consider is that during playback, a student might want to pause the playback, bring up this model of the prostate, look around, observe it, make sure that they know what they're doing before taking the model away and resuming playback. So we believe that our system has a number of advantages over physical presence, mainly in that while it tries to emulate the immersion and interactivity of physical presence, we also try to sort of enhance the scene with things that would be difficult or otherwise impossible with physical presence, such as playback and annotations. At the same time, we strive to make the technology accessible so that somebody who even has a cursory understanding of how VR works should be able to put on the headset and start exploring the scene right away. Additionally, the system is fairly extensible. So really the only thing that differs between procedures is the 3D reconstruction data. So you can imagine that some sort of distribution network could be made where you can download the reconstruction data for a new procedure, and then everything should just kind of work out of the box. Unfortunately, we've also run across a couple of limitations. I've talked about how we've only been doing this for prostate biopsies, though we hope that this will change in the near future. So when I came in August, I didn't really know a whole lot about 3D graphics. So we thought that the best way for me to get going quickly would be to use Unity, a 3D game engine that sort of abstracts away a lot of the details with rendering so that you can focus on, in Unity's case, making games. Unfortunately, as the months progressed and I started to learn a little bit more, I came to realize that Unity sacrifices a lot of control and in some cases performance to meet these goals. So in fact, we've actually noticed a noticeable decrease in frame rate as compared to something like, for example, OpenGL. And then finally, some aspects that I mentioned earlier, namely the poses of the annotations and the models, are actually hard-coded due to the fact that we, the programmers, know a priori the coordinate system that we're dealing with. So we can hard-code them so that the annotations, for example, are along the wall or the model is wherever we chose to put it. But if we just tried to port this immediately to a different data set, then they would appear kind of randomly. So this is definitely a limitation that we hope to alleviate. So in the short term, we'd like to make this even easier to use. This would mean, in practice, introducing a configuration utility so that a physician can, for example, place the annotations in the models wherever he deems to be best suited, so that we don't have to try and anticipate where these things are going to be located for different procedures. This would probably necessitate a better controller than we currently have. We currently use a wireless mouse, which was great for sort of rapid prototyping, but seeing as we only have sort of 2 click buttons and a scroll wheel, the limited number of degrees of freedom there certainly limits us in how we can enhance the scene. In the long term, we'd like to maybe focus on having more than one participant at a time. So you can imagine that maybe you and your buddy have your Oculus headsets and you're viewing the same procedure, and you maybe want to do this over a network so that you can chat on Facebook about prostate biopsies or whatever. And then finally, there were a number of other ways that we had considered enhancing the scene. One of them, which we deemed infeasible for me to do in my time period, was introducing transparent anatomy. So it would be probably really useful if a student could cut away at a portion of the mesh, and rather than being nothing there is relevant anatomical structures exactly where we're expected to see them. All right, thank you, guys. Yes.
What is the extent of the interactivity in the virtual reality? Are you only walking around and observing, or are you actually affecting?
So you're walking around and you're observing it, but it's interactive in the sense that you can control how the procedure is played back with those playback controls.
Okay, yeah. But when you said the phrase "cutting away at the mesh,"
so that's something that that would be something more interactive, like you're talking about, but that we deem to be sort of infeasible with our time frame. Yes.
So, what's the limitation that's keeping the dynamic part of the scene from being more detailed? Because it seems like in some procedures you would lose a lot of the detail that was.
Yeah. So the frames that I showed you actually don't incorporate a lot of techniques that Ming Song's paper used, like time-based integration, which actually significantly increases the quality. That's pretty much just the raw reconstruction, without anything like texture mapping or time-based integration. So time-based integration would be, for example, if there's a camera over there and my waist is occluded by this monitor at this point in time, it can incorporate the fact that later in time my waist is visible, so that at any point in time I've got the full reconstruction.
All right.